All right, so now let me explain how support vector machine works. So in fact, to construct a support vector classifier, which is the same thing as a soft margin classifier, one does not need training observations themselves. One only needs pairwise distances or pairwise inner products of observations. Now, to understand why, you need to have taken this basic optimization course. So if you have taken this basic optimization course, you can just read some notes about it and figure it out. So why we only need these pairwise dot products. This has to do with the dual problem and with Lagrange multipliers. If you have not taken the basic optimization course, then it's not a big deal. Just forget about it. It's not going to be tested, right? But just believe me that you need these pairwise dot products. So if we are going to enlarge our feature space, right? So then it means that to train our support vector classifier in the enlarged space, we need inner products in the enlarged space. But the trick here is that we do not actually need to know the enlarged feature space itself. So we do not need to know this. It is enough just to know this the dot product, how to calculate the dot product in the enlarged space if we know the vectors in the original space, right? And this function k, which shows us how to calculate the dot product in the enlarged space if we know the observations in the original space, is called a kernel. So, and the trick is that in order to compute this inner products, we do not need to know f. So we can work with k. Right, so a linear soft margin classifier is given by this formula. It is also the linear support vector classifier. So soft margin classifier is the same thing as a linear support vector classifier. So a support vector machine is one more added thing to it, so non-linearity, right? So support vector machine is a soft margin classifier that looks a little bit different. So we are going to replace the inner products in the original space with the kernel function, which, as we know, it is the inner product in the enlarged feature space. Okay, so thus support vector machine is soft margin classifier plus kernel trick that allows us to compute inner products in the enlarged space. Right, and we do not explicitly construct this enlarged space. So we just apply this kernel function. So let us look at a few examples. The first, our example, so the method helped us to separate the iris classes. This is the enlarged feature space. Now, this is the kernel, so this is just the dot product in the enlarged feature space. Well, sorry, I have used y here. I probably should have used x instead, but I hope it is all right, right? So this, usually instead of y, we should probably really use x1 and, sorry, x1 and x2 probably. But I hope that it is clear. Right, so, and the nonlinear classifier is given by this form. Now it is nonlinear because it is nonlinear in x1 and x2 because of this nonlinearity. So here is another example. So suppose that our kernel works like this, right? So we take the sum of squares, so product of the squares of the first entries, plus the product of the squares of the second entries, plus the double the product of all the entries of the two vectors. Right, so this is the same as considering this function from R2 to R3, because now if we have this function, then you know, we can if say we have z1i, z1j, this is going to be x1i squared, this is going to be x1 j squared, and then we are going to, when we calculate the product, we are going to multiply them, and this is going to give us the first term, and so on, right? So the inner product in this enlarged feature space R3 is the same thing as the kernel function in the original space. All right, so if for some reason we wanted to transform our features, so instead of taking the original features x1 and x2, we wanted to change them so that we have 3 new features, x1 squared, x2 squared, and the third one is square root 2 times x1, x2. Then it is the same thing as considering this kernel function. So example 3. So suppose that, again, so P is 2, and we want a decision boundary, a quadratic decision boundary, right? So of this form. I'm claiming it, so, well, this is the same thing as enlarging the feature space using this function from R2 to R6, right? But at the same time, this is the same thing as considering this kernel. So why is this so? So let me just rewrite this. So this is actually the square of the sum of 3 terms is the sum of squares is going to be 1 plus, you know what, let me write not exactly this, but let me write k of x and xi. So where x is a new observation, so new observation, new data. Okay, so this is going to be so, which means that I'm going to replace xj in the formula for the kernel with just x, right? So I'm going to have the sum of squares. So this is going to be like x1j squared times x1 plus x2j squared. Sorry, I, not j. Of course, it should be I, not j. So I times x2 squared plus I'm going to have twice the sum of the pairwise product. So I'm going to have 2 times x1i times x1 plus 2 times x2i x2 plus I'm going to have 2 times x1i x2i x1 x2. Okay, and let me just compare it with, so I have 1 here, so here, and also the constant term here. I have the quadratic term here, x1 squared, I have it here, and I have it here. So I have the other quadratic term here, x2 squared, here and here. I have the linear term here, here, and here. I have the other linear term here, here, and here. And I have the mixed term here, here, and here, right? So all the terms are here. So which means that later, when I write my final classifier, which is a linear combination of this, so this is going to be something like alpha I times this. So when I add them all together, and when I collect everything with x1 together, everything with x2 together, I am going to get something of this form, right? At the same time, if you think a little bit about how to compute in this kernel and versus the original inner product in R6, then computation that uses the kernel is more efficient. Why is this so? Because if you look at how many operations are we going to actually compute when we compute this kernel, right? So we are going to have two plus signs, right? So two plus signs. That we are going to have two products. So first, second product, so plus two products, and plus one square, and square is the same as a product. So I'm going to have three product signs. So I have two additions and three multiplications. So overall, I have like 5 elementary operations. While if I compute the inner product in R6, well, the first entry is always 1, right? But I still need to compute 5 pairwise products like this entry times the same entry in the second vector, this entry times the same entry in the second vector, and so on. So I'm going to have 5 multiplications, and I'm going to have 5 additions, because after doing 5 multiplications, I need to add everything together. So plus 5 additions, so I have 10 operations in the end, right? So which means that computation that uses the kernel is more efficient. So, and of course, the higher the dimension of this feature space, enlarged space is, the more efficient is the computation of the kernel as compared to computation in the enlarged feature space. Okay, so this is another advantage of using the kernel, because we do not need to actually know our function f, and because it is more efficient. Okay, and one last example is if our kernel is so note that this looks like the probability density of the standard of the normal distribution. So only instead of x here, I have xi minus xj, right? So which is why it is called a Gaussian kernel. So sometimes, right? So now if you rewrite this using the Taylor series, you will see that this is actually like the sum of infinitely many terms. So which essentially means that if you think of this as enlarging our feature space, it means that essentially we are enlarging it by an infinite dimension. So we're going to embed our original feature space in our dataset into an infinitely dimensional space. And of course, the direct computation in the infinitely dimensional space is just impossible. Right? So which means that using the kernel is the only way to tackle this problem. But using the kernel actually works. Okay, so this is all for this part 7. So now please do the quiz.